complex number calculus. Here we learn what happened to the calculus if variable is complex number. This whole subject is like one semester's course, so here we just concentrate on understanding overall pictures. We skip the details like the proof of the claim, which you can find in the math book. So complex number variable has a two variable, x and y, right? And the z complement is x minus yi. Okay, so fz is turned to be u xy plus v xy, sorry, this is wrong, I. So if you add z plus z complement and divide by 2, you get the real part of the z, and imaginary part of z is you subtract complementary numbers and divide by 2i. Polar coordinate will be is actually r e to z I theta is r cosine theta plus I sine theta, right? So it's like x, y, and you have r and theta. So this is yi. So this is a basic variable. Now we need to define the limit first. Limit is defined according to this epsilon delta method, which is same as the previous calculus. This is a continuity issue. Suppose you have z0 and z is nearby. You check the distance. This is the distance. So the method to describe this continuous function is, say this point is fz and this point is f0. So for any small epsilon, you can always find the delta such a way z minus this distance get close, you can find it. If it's discontinuous, for example, the function is like that, this small epsilon, you cannot find the delta for this, so it's a discontinuous function. So if the function is continuous, then we can do limit. And for a complex number, we write LT, capital. Most of the function complex number, we use capital letter, LT, okay? So derivatives is defined by this. Now, I hope you remember in the derivative section, sometimes you have not smooth function. This slope and this slope is different. So if you take a derivative of fx, you will have two different value here. So derivative function become discontinuous. This is not smooth. The same analysis is done. The smooth function is called analytic function in the complex variable. It has a unique derivatives. So there are two conditions for that. Within a region R, so you take x, y, I, and region R, four functions below are continuous. This is continuous. Okay. Then Cauchy-Riemann equation. I'm not sure how to read this Cauchy. It's a French name. It's Louis Cauchy. Could be different name, but this is the condition. Second condition. This is gonna be necessary and sufficient condition to be analytic function, which has only unique derivatives on every point within R. Okay. This name, you know this. This is the Kirchhoff's theory. I was reading in German way, Kirchhoff's. Then the student asked me why you read this strange way. Well, it's not strange, it's a German way, but we agreed to use the English way to read it, Kirchhoff's theorem. Okay, so I'm not sure about this either, so probably the English way to read it is good enough, Cauchy. So analytic function form the orthogonal system. This is a characteristic of analytic function. What's happened is, what is orthogonal? U and V, we use a constant and make a group of curve, and they intersect each other orthogonally. Okay, the proof you can find it in a math book, and transformation is called mapping. You have x and yi, u and vi. The region R change to different region. Okay, it's called mapping. Now, this implies that the complex number calculus can be used for coordinate transformation. Okay, now Cauchy's integral form. We define the derivatives. How about integral? Say fx is analytical within and on a closed curve C, and A is any point within C. We take an integral loop. So this fz is analytical. You take any point A, and we take integral along this boundary, the A. This integral becomes fa. Okay, this is a very important integral formula. And now there are various integral techniques introduced for the using this. One of them is the residue theorem and stuff. It's as I said, whole semester's class. We cannot cover everything here, but I hope you get some idea. So I hope you enjoyed listening to this video. So please check out the videos, and if you like, click subscribe.